Behold, the AI laser turret. For use of inverse kinematics with two hinges, this thing can aim at you, shoot at you with a cooldown, and once you leave its target area, it does this cute little idle animation where it looks around trying to search for a new target. This thing is absolutely sick. It has smooth animations. It looks at you. It does all the stuff that you want it to do. So, in this two-part video series, I'm going to be teaching you how to make this. This thing involves a lot of technology. We use hinge constraints, vector 3, angle that method, and it almost uses inverse kinematics basically. And then for the AI part, we do some overlap queries, we do a lot of raycasting, and a lot of cframe math. So if you're interested in any of that, or you're just interested in having a sick turret to defend your base in your game, just stay tuned and watch this video. It is kind of tough, so I would warn you, but I cover it pretty well, or at least in my opinion, and it should be able to teach you everything you need to do to not only use my turret model to make a turret, but also make your own AI turrets in whatever style that suits your game. So in this video, we're going to be covering the model setup and the basic aiming, so aiming at a specific direction. In the next video, we'll be covering the shooting and the AI portion, so stay tuned for that. I hope you're excited as I am to get into this, but without further ado, let's jump right in. So this is the model that I will be using to create my AI laser turret. It will be in the description if you want to follow along with me setting it up and getting it working. But if you want to make your own, there are a couple little requirements that you have to do for this tutorial for it to work the best it can. And I encourage you to make your own because it'll be a nice learning experience and it'll better fit your game. So my AI laser turret in the Explorer, let's drop it down. You see there's a couple different parts. The base is just the base of everything. It won't move. It just sits there. Make sure that thing is anchored. Mine is anchored. Good. Can't collide. Doesn't really matter. Should probably be on. And then we have two sub models. We have housing, which is like gun housing. It'll move like up and down for elevation and depression. And then we got the platform, which will rotate around like a turntable. So inside of the platform, you notice we have another base part. And by the way, these base parts are the primary parts of their parent model. So this AI laser turret, the primary part is the base or the platform. The primary part is this base. This base is also where the model will be rotating about. So when we eventually make a hinge, it'll rotate about this base part and the hinge will be there. So let's go into our housing. This is where there's some important key notes. So to start off, we have to make sure that our barrel, the gun barrel, whatever your gun will be shooting out, is in line with the pivot, like axis of rotation, where it'll be rotating up and down. So make sure they're exactly in line. That's because we want the gun to aim properly. And when we measure the angles, we'll be doing it relative to a part that will be at that point, and we want to make sure it's at the appropriate angle to shoot properly, because if this barrel is kinda out of line, it'll lead to inaccuracies when you're shooting your gun. So make sure that, and also make sure the base part is that pivot point, the primary part is that pivot point, because it'll allow you to do better testing, and it doesn't really matter that much for the actual functioning since we'll be using constraints, but it'll be better. So, speaking of that, let's go to our housing, make sure that base is that primary part because you'll be able to rotate it up like this and verify that the bottom of your gun does not collide with the platform. Should not do that because your gun will need to be able to go this high. We will be handling depression in the code. So the gun does not need to be able to go all the way down because we'll handle that in the code, but it will need to be able to go all the way around. So that's that. Everything is good. And make sure that anchored is set to false on all of your parts except for your base. So moving on, the next step is going to be to add our hinges. So let's start with the platform. We're going to move up the platform up a little bit. There we go. We're going to go to model, create hinge, and I have a video on hinges going more in depth if you want that. And just arbitrarily place the hinge. Doesn't really matter if it's centered. So just place that and then place this somewhere. but don't really know, don't really care. Because what you're gonna do is you're gonna go to your attachment, and if you cannot see these attachments, make sure to go to Model, Constraint Details, and that'll allow you to see the attachment, which should be nice. And then you're gonna select that, and then you're going to go to the position, and depending on what part this is, since this is the cylinder part, we're going to have to play around to see what values we actually want. Because we want it to be centered horizontally, but the vertical offset should still be there. So if I set this to 0, that's not what we want. Then I know I need to set both of these other values to 0. Because when I set the X value to 0, it moved up. I want it to be central. That's central, and it's still down. Like, it's still at the edge of the part, which is what we want. We're going to do the same thing for the bottom. We're going to make sure. There we go. That's exactly it. And if you've done it correctly, they should be like vertical on top of each other. That is also assuming that your housing and platform are perfectly centered on your base part, which they should be. So now we can select both of them, move them down like that. That's good. And the reason it snapped like that is because I have my model move mode set to physical. I would turn that back to geometric for testing purposes, but you can leave it at physical to test it, which we will do in a moment. But now let's go to our housing, and we can move this off to the side because we need to add another hinge. I'm going to go to create hinge, and we're going to select our little pivot access point here. Doesn't really matter where. And since this part I'm doing is a union, we have 0 snappage, which is kind of annoying. But what we can do is we can go to this part, double check that it's centered. It's almost centered. We got our 0.071. But now we center it, and now we can go to the world C-frame, not just the normal C-frame, the world C-frame, copy that position, then go to that attachment, paste that into the world C-frame position. You'll notice it moves back to where the part is, and we want to just drag it across the edge of the part that we want to connect to. There we go, that's perfect. And move this over there. So, and if you've done it correctly, there should be no red arrows indicating that your constraints are kind of off. And that's all you need to do. Keep in mind that I selected the base of the platform and then clicked the bottom part that I want to connect to. I selected the base of my housing and then clicked the platform. Just some key steps, note. But if we were to run this, what would happen is all the parts would fall apart because they're not welded together. I have a video on weld that go into more detail if you want to check that out, but they're quite simple. So what we need to do is we need to weld the platform to itself and nothing else. So I'm going to go to platform, select all three of the union, or the union, and the base, and then I'm going to go to create weld to create welds. And then if I want to see these welds, make sure show welds is toggle. You can see everything is stuck to each other, which is great. And I can do the same for my housing by selecting all of these parts. Go to create weld, boom. There we go. And then that's that. That's pretty cool. And so if I were to run this, everything should be connected and should be chilled. Yeah, so there you go. You see how the gun kind of depresses? Yeah. But that's exactly what we want. And then if you want more testing, you can go to model mode or physical or physical move mode. And you can kind of like drag this around and you can see how it rotates. You can drag it up and down. Be cool. So I just use Control Z to reset it because I don't really want that extra movement for now. So that's all the physical stuff handled. But before we can do anything else, we got to remember to go back into our hinges. This bottom hinge, I'm going to rename the yaw. And I'm going to set the actuator type to a servo. And then I'm going to set the speed to something like 5. The max torque, I'm going to make this a big number, like 50,000, because you need a lot of torque to get things moving properly. Set that to a big number, as large as you need it. And leave the target angle. We don't care about that. I'm going to go to my housing, go to my base, and my other hinge. Rename this to the pitch hinge. Because if you ever played an airplane game or like looked at airplanes, you know, like pitch and yaw. Yaw is like kind of the horizontal motion, pitches up and down. That's what we want for the hinges. We're going to set the actuator type to a servo, and then do the same here. Servo max torque to be to like 5. torque to leg, 50,000. There we go. So that should be more than enough. We may have to adjust those torque values later, but that should be good enough. So now what I'm going to do is I'm going to create a completely new part just in the workspace. Actually, we're gonna make this part a sphere. Make it um transparent. Doesn't we don't need to see it. Make it small, 111. And this part is going to be our reference part to calculate angles for our hinges. So I'm going to name this part ref. And this part is going to have can collide off and anchor to true because it's only there for the code. It's not necessarily used for like actual visual stuff or physical stuff. But we need this part to be centered at the point at which the model will be rotating always. And that is at this fulcrum, the base of our housing, which I'm going to select by alt clicking it through the model. I'm going to copy the position. I'm going to go back to my ref part workspace, position it exactly where I want it to, right there, by using Control C, Control V to copy paste that. We're going to move it into the AI laser turret so it's underneath the model. And then to double check everything, we're going to run it once again, make sure everything still is physically simulated. And you'll notice that the model's no longer dropping down because we set them to servos and they're holding up everything in position, which is good. That's kind of what we want. And our ref is not interfering with anything. So that is good. One more thing is I'm going to check the refs by right clicking it, show orientation indicator. Make sure, yeah, the front is facing the front of the barrel, which is just something that we want to make sure of. Okay, that's the setup. It's a lot of setup, but I want to make sure you guys can get this because I remember when I used to watch these videos myself and people didn't tell me how to properly set things up. It was nasty and we don't want that. I want you to know how everything should be made. So now we're going to create a test part, another sphere. I'm just going to make it like testing green. That'll be our testing green. Make it a neon because I love neon. Make it mostly transparent and make it a and then we're going to make this a little smaller. There we go. This will be named our target part. This is where we're going to be using for testing before we get it, like the AI actually working, just a part that we can aim at. Okay, so now let's go into the turret and let's get actually scripting. This is what you're here for. It's not about all the setup, but the setup is quite important if you want easy scripting. I'm going to rename the script to the turret script. I'm going to zoom in so you guys can see. We're going to do a couple things. So first of all, we need the turret. Turret will be equal to script.parent. Now we need to get our reference part, of course, which will be equal to the turret.ref. And then our hinges. So I'm going to get the yaw hinge first, which will be in the turret, in the platform, in the base, and the yaw hinge. There we go. Then our pitch hinge will be the same. Turret.housing.base.pitch hinge. There we go. So we got our pitch, we got our yaw hinge. Change these references as needed in your own model. And now all we need is to get our run service because we're going to be using a run service event in just a moment. The game get service run service. And then we're going to need our target part. Say local target part equals workspace dot target. There we go. And now we're going to do run service dot stepped. Connect a function with elapsed time. I'm going to say ET and delta time DT. And in here, the reason we're using stepped is because this comes before the physical simulation step of each frame. So we're going to be setting the target parts target position, or the hinges, I should say, their target angle every frame. So we want them to be set before they're actually simulated, which is what we want. And this step runs every single physics frame, which is okay. And then outside of that, we also need to get a direction. And this will be equal to initially just vector3.x-axis because we need like an initial direction. This is where we want to point. But obviously, for testing, we're going to be pointing at the target part. So we're going to say local, or we're going to just say direction. We're going to reset direction every physics step to be equal to our reference.cframe point to object space, and we're going to send in our target part dot position. I have a video on this as well if you want to check that out. But basically, we're converting our target part's position to relatively to our reference. So we can actually aim at it no matter the orientation, because the goal is to be able to rotate our turret in any direction, like the base and whatever, and it'll still be able to aim at the part. That'll be really good for stuff like vehicles, and if you ever want to make the turret move or just be in a weird angle, it'll be good. So let's go in and let's do the yaw hinge first of all. So I'm going to start by getting the flat direction. So flat direction will be equal to direction times vector3 dot new 101. So what this does is we flatten our direction. We take our x, y, and z, we multiply the y by 0 so it disappears, and we keep the x and z. So that we have a flat direction, because when we're calculating our hinge, our yaw hinge, we don't care about the up and downness because we're only looking at it from a bird's eye view. We only need to know where where it's actually pointing to. So like the flat direction here would just be pointing directly to the target part. We don't care about up and down. And the way we're actually going to get that angle is we're going to say yaw hinge dot target angle is equal to math dot degrees vector 3 dot, let's do the x, or let's do z axis angle, or colon angle, with the other vector, which is going to be our flat direction, with the axis as the vector 3 dot y axis. There we go. So what we're doing here is we're calculating the angle between the axis, which in this case is just the axis facing like that way or something, and the flat direction, which will be pointing towards our part. And I have a video that goes much more in depth into vector 3 angle if you want to check that out. But all you need to know is just between the z-axis and the flat direction, because we need like a reference to calculate it against. We're sending the axis so we get a signed angle. What that means is we can do a full 360 degrees because it goes from 0 to 180, and it'll go back to 0 and then go back to 180. But if we add in an axis, which is just the y-axis, so the axis which is rotating through, we'll get 0 to 180 and then to negative 180. So we get all the full 360, even though it's 180, but positive and negative, we get 360. So if we were to just test this out now, and also we have to convert it to degrees because this gives you an angle in radians. We want to get it in degrees because the hinge actually works in degrees. Let's run this, see if it works, see what happens. So you'll notice it's facing back. We can't have that. It's facing backwards. We need this gun to point towards the thing. So what we're going to have to do is just negate our flat direction. So let's play this. Flat direction is negated. Boom. We're aiming. The yaw is aiming. That's perfect. So your gun might be different than mine, and that's okay. Because between a combination of negating this direction here, or negating math.degrees, or changing this vector3.z-axis to vector3.x-axis, you will be able to get your turret to aim in the proper direction. So those are the three things that when you change them will have an effect. So if I change this to negative math.degrees, you'll see now that it kind of rotates opposite of our part, which is not what we want, but depending on your gun situation, you might have to do that. And then if I change the z-axis to x-axis, it'll just make it go out of phase, like 90 degrees to the side. You see how like the side is pointing there? That is a symptom of having the wrong axis. So let's set this back to the axis. And then you can change your flat direction to flip it around if it's facing like the exact opposite direction. So depending on your gun, you may have to do that. Now, before you move on to the next step, you want to make sure your barrel is pointing where this is. And once you have that, you're now good to move on to the pitch. Because honestly, I don't want to teach you guys how to follow exactly along with my model. I want you to be able to adapt this to your own game. So you might have to do some special debugging. But I've given you the tools: negate this, or change this to x-axis, and you should be able to get everything. Push comes to shove, you can always add a vector, a number offset to the degrees, because this is in degrees from negative 180 to 180. You can always add like 90 degrees. I don't have to do that. I've never had to do that, but if you're really getting desperate, you could try doing that. I'm not sure how it would work, but it's just other options. So now we pitch. This is a little complicated because what we want to do is we have our flat direction, we have our direction, which like would, in this case would just be pointing here, pointing down, and we can calculate the angle between them, but we need an axis. And this axis will be pointing out perpendicular. So how do we get a perpendicular vector to our flat direction and our direction? we need to use cross product. So we're going to do axis equals local axis equals vector3 dot y-axis. So since it's a local space, we can use the y-axis. We can cross that with the flat direction. So the y-axis will be pointing like up like this. Flat direction will be pointing out like this. We'll get the cross product, which will give us a vector pointing out to the side. And then in here, we want to go set the actual pitch hinge equal to math.degree. Once again, math.deg. I'm going to do flat direction now. The angle of the flat direction. So flat direction angle in the direction using the axis as our axis parameter to our vector 3 angle. So the flat direction goes like out this way. The direction goes down out that way. We need the angle between there using the perpendicular bit as our reference. So if we run this, let's just see if it works first try. Does it? Oh, it still doesn't even. Oh, also, our part is not anchored. We need anchor. We need to anchor our target part. So I set that. Didn't really do much. Let's go double check it again. Oh, you know why? Because I set pitch hinge, not the pitch hinge dot target angle. Stupid me. So pitch hinge dot target angle equals this stuff. Debugging with B-Rising. There you go. So look, the points of the thing. Wonderful. This is exactly what we want. We can move it around, move it up and down, and boom. So pretty, isn't it? So cool. So again, if this doesn't work out, change the same parameters that I did. You can set your direction. You can put a negative here, put a negative in front of here. You could change. That's really all you could do for the pitch. So if the pitch ain't working, go back and change your yaw. Try to fix your yaw first so the barrel points properly, and you should be set to do your pitch properly. I hope that helps. If you have any comments, please put them down in the description because this is complicated, but it's a lot better to learn this yourself so you can apply this to your own games than to follow me blindly. So learn how to do that, evolve, and just work with it. Because you don't need to understand how all this math works. All you need to do is understand how to play with numbers and play with constraints to get everything working nicely. Because they provide you all the methods and they get you to do all that stuff. It's always absolutely wonderful. So, using this framework that we have, the reason it's so complex is like it's easy to do this on a 2D plane. What if we take our AI laser turret, we move this thing up, and I change my mode to geometric. There we go. Move this thing up, and we were to like rotate it. Like no, surely it wouldn't work. But if you look at that, it does. It's still by some magic, by some miracle, we can still aim directly at that point. You see, the barrel's loaded. It's ready to go. And we're aiming directly at that point. It's absolutely phenomenal. You can put it wherever. It looks exactly at it. We can move this up. It still reacts properly. We could rotate this fully upside down or like fully sideways like that. It still does the trick. So if like you look at the barrel through it, there you go. You can see it's lined up perfectly. So this is because we're using our relative object space. Everything is relative to our turret, and we're just kind of converting everything from the world to relative. It just works. It's beautiful. Complex vector math, but it gets the job done. I know this is a lot, but that's why I'm splitting this into a series. So that's about it for this video. I really hope you enjoyed learning how to do all this stuff. It's complicated, but it looks freaking sick. Like you can't tell me this doesn't look really cool because it's a freaking gun. Pointing physically simulated it has travel time too. It doesn't snap exactly. It has actually like moves and it looks very smooth animated well both on the client and the server because we're using these physical constraints and it's dead on accurate. And that is wonderful. So there will be help in the description with a bunch of other videos because it builds on a lot of stuff that I've already taught. There will be the model and the finished product of this video will also be in there to check out. And yeah, so stay tuned for the next video. Like and subscribe if you enjoyed it. Please comment down below any questions or suggestions. But with that, I hope you have a nice day and goodbye.